here to give a talk about our work on crossing numbers. So it's a subpolynomial approximation algorithm for graph crossing number. And this is based on joint work with Julia Chudroy and Subpolynomial Mahabadi. Julia Chudroy was my advisor at TTI. I was a graduate student at University of Chicago under Julia's supervision. And Subpolynomial Mahabadi was a research assistant professor at TTI. Now she's at Microsoft. So this is a combination of two results, all on the same problem. Okay, so let me first introduce what the problem is. So the problem is called graph crossing number. The input is a graph, which consists of a set of vertices and a set of edges connecting them. And the goal is to compute the drawing of this graph into the plane with fewest crossings. Okay, so what is a drawing of the graph? A drawing is simply what you can imagine about it. It's simply a mapping formally that maps vertices into points and maps edges as curves that connect corresponding endpoints. Okay, so this is basically a mapping. And the crossing in this drawing is basically intersection between two curves. Okay. So ideally, we want to sort of visualize the graph. And in this goal, we basically want to draw the graph into the plane. And we want to see the graph as clear as possible. So in this case, we want to minimize the number of crossing because crossing confuse things, makes things more complicated. Okay, and this is the goal, the very initial goal of this problem, what I want to achieve. So for example, if your input graph is K4, a click on 4 vertices, then this is a drawing of K4 in the plane. And this drawing contains one crossing, which is this intersection. Okay, so before I go into the detail of this problem, into the algorithm, need to specify a few things in what is a legal drawing. Okay, so a few things are indeed prohibited. For example, we do not allow the image of a curve to go through the image of a vertex like this. This is not allowed. Okay, it has to be as simple as it can. So it does not. It's not an edge that contains this vertex, so it cannot pass through it. And also, we do not allow 3 curves to go through the same point. Okay, it still need to be as clean as it can. Okay, so basically, this is some way that you want to sneak by some crossing. You try to cleverly reduce the number of crossing, but this is all forbidden. Okay, has to be very simple. So actually, we do know that K4 is a planar graph, right? So if we draw the graph differently like this, then this is a drawing with no crossings. Okay, and this is also what we call a planar drawing. Okay, so the crossing number of a graph is simply defined to be the minimum number of crossings in any drawing of this graph. Okay, so this is the definition of the problem, and the goal is to compute this number as well as a drawing that achieves this number of crossings. Okay, so this problem has a very long history. Actually, I think it was introduced by Paul Theorem in 1940s during World War II, where they want to design real roads to facilitate transportation, and real roads, crossing is a dangerous thing, so minimize the number of crossings. And then it has been studied extensively, and it has found various applications and connections to other areas, also industrial or theory part, graph algorithms, graph visualization, VLSI design, incident geometry, etc. Okay. And according to a bibliography maintained by Vertol, it has been studied extensively, and by 2014, already 700 papers were written on this topic. So both from math part or from algorithm part. Okay, but despite all this effort, this problem is still far from being understood. Okay, especially from the approximation perspective, which is the perspective that we're going to take today. Okay, from the approximation algorithm. So, and one interesting part of this problem is that we basically cannot hope to employ any well-known type of algorithms. For example, if we want to write an LP, write an SDP to characterize some lot of combinatorial problems, but just not this one. So think of how you characterize a crossing. It's basically very hard to use some linear constraint to characterize, okay, these two edge cross. So basically, you need to work from first principles. Start from scratch. Okay, so let's look at some previous results on approximation side of this problem. Okay. So for general graphs, there are just no non-trivial approximation algorithm known. Okay. And the strongest hardest result is only APX hard. which rules out 1.0001 approximation as long as p not equal to np. Okay, for a very small constant, like 1 plus that. But we do have one beautiful result about this crossing number, which is called the crossing number inequality. So this inequality says if the number of edges is larger than 4 times the number of vertices, then the crossing number has to be on the order at least m cubed over n squared. Okay, so this was independently proposed by Itai, Cheverton, Newborn, Simirdi, and by Layton. Okay. And I would like to present a very beautiful probabilistic proof of this crossing number theorem. Okay. As I'm told that this talk is supposed to be longer than what I prepared, so let's fill in some details here. Okay, so crossing number inequality, as long as number of edges is larger, the crossing number has to be very high. So this is the message. Okay, so first, for a planar graph, we know that it is very sparse. So how sparse for a planar graph? So if a graph is planar graph G, then its number of edges, M, is less than 3 times the number of vertices minus 6. Is this known to everyone? Is this okay? Actually, we will just be doing something very loose because it's off order, so we can ignore something like this. Okay, so M times less than 3n. Okay, so if a graph G, let's say it is drawn in some optimal way, okay, a graph G, and this is a drawing of G that contains CRG crossings. Okay, CRG is a crossing number of this graph. If we look at this graph, and for every crossing, we delete one of the edges that participate in this crossing, then what we get out of it is a planar graph, because we have basically dealt with all the crossings. Okay, we start with an optimal drawing. For every crossing, take out one edge. The remaining graph is planar. So what is this saying is that if we start with the original number of edges, take out at most CRG edges, then what remains is a planar graph. Okay, so less than 3n. Okay, so this is basically true for every graph. Okay, now we're going to do some probabilistic thing. Okay, so we're going to do, let's say we're given a graph G, and we're going to take a subgraph G prime that is obtained from G by keeping every vertex with probability P independently. Okay. P is some parameters that will be fixed later. Okay, so picking every edge independently with probability P, and also what edge are still remaining in the graph. It is if both endpoints remain in the graph, then the edge remains in the graph. Okay, so this is like a subgraph that this is a subgraph that we extract from G, and we are going to apply like this inequality to this, although in a very expectation way. Okay, so what is the number of vertices that it has? It is n times P. Right? So basically, we are taking the whole this inequality in this expectation form. Okay, so what is the expectation on the right? Every vertex with probability taken into it is NP. It's not non-deterministic polynomial, but it's NP. Yeah. Okay, so how many edges are there? For every edge, as long as both endpoints remains, the edge remains in the graph. Right? So it is M times P squared. It is not independent, but by linearity of expectation, we can still calculate it. Right? Okay, so what about the crossing number? For every crossing involves 2 edges. It has to be the case that both edges remain in the graph, that the crossing can remain in the graph. Okay, so yeah, maybe let me try to first rearrange this like this. Okay, so we try to first rearrange it like CRG is larger than m minus 3n. Okay, and we're going to take that expectation of this. Okay, and yeah, what is this expectations? Okay, so what we have shown, this is minus 3n p, and this is m p squared. Okay, so the crossing is basically every crossing stays with probability p to the fourth actually. Okay, so this is CRG times p to the fourth. Okay, we need to be a little bit careful with this. So this is the number of crossings in a drawing that we can get. And it's larger than the actual crossing number of the remaining graph because we have obtained one solution and CRG is the best solution. Okay, so this is actually larger than some expectation of CRG, larger than this. And we are going to omit the things in between, just this. Okay, this is just some like rigorous steps, but this is what we get. Okay, eventually what we said is this. We just need to set P equals M over 4 in let's see, 4n over m, sorry. And what we get is just this. Okay, let's maybe do the calculation throughout that. So let's say this is -2 -3, right? Like divided by p to the 4 on both sides. And what this is, n times p to the -2, and the p is 4n over m. So it's m over 4n squared. And this is -3 times n times m over 4n cubed. And now you can see that it's all m cubed over n squared, m cubed over n squared. And this is at least like m cubed over n squared. And I believe the parameter here is 64. So this is 1 over 16, 3 over 64. So, yeah, so this is the crossing number inequality. Okay, so it's a beautiful proof. I think in the first two papers that figured this inequality out, it's not using this probabilistic proof was discovered later. So it's a very beautiful one. Okay. So, but the message, like it translates, it conveys to us is that as long as the graph is a little bit dense, the crossing number has to be very high. A little bit dense, okay, dense than like 4 times n. Average degree is larger than 8 or something. The crossing number has to be very high. Okay. So as you can imagine, if the graph is a clique, then basically every pair of vertex has to cross. Every pair of edge has to cross in like the optimal drawing, even if in the optimal drawing, almost every pair. Okay. So the most interesting part of this problem is really when the graph has a very small number of crossings drawing, but it depends on whether or not we can find it. Okay. So we like the very dense graph, whenever you draw it, it's almost optimal, but it is a mess. Okay? The most interesting part is it has a clean drawing, and if we can find it. So it is therefore reasonable to look at special families of graphs where the graph is just relatively dense. And in particular, we look at low degree graphs where the max degree is bounded by some constant or some slowly growing function of n. Okay, seeing here, just think of max degree delta to be some polynomial or n to the little of 1. Subpolynomial C. Okay, and this is the class of graphs that we're going to study today. The crossing number on this type of graphs. Okay, so even for this type of graph, still not a lot is known. Okay, so the strongest approximation result for a very long time stays just the O tilde n approximation. Okay, so normally for a combinatorial problem, O tilde n is trivial, or like that, right? But this is like the best. It's still non-trivial and takes a lot of effort to get it, and remains the best for a long time. Actually, what they can get is given a graph. Okay, this is for bounded degree case. Okay, what they can get is an approximation algorithm that, given the graph G, computes a drawing with n plus CRG crossings. So it is in some sense a very nice result, as long as CRG is sort of n. Then what you can get is just a constant approximation even. Okay, but there's still a lot of room for improvement. For example, when CRG is very small, okay, CRG is like a constant. This is just an ON approximation, very bad. And this is the room that we're going to prove. If time permits, I can probably present this algorithm later, but this is sort of a detour from the main line. So I want to like sort of put it to the end. This is also a beautiful algorithm, not as simple as this, but still it's a beautiful one that's worth presenting. Okay, so yeah, the strongest, hardest result bounded degree graph for a long time is still only APX hard. Okay, so it's still probably just a 1.001 is not possible. And there's a big gap between just by 2004, like that. And later on, there's a breakthrough sequence of 2 papers by Chuzhui, Makovic, and Theopoulos, and then by Chuzhui, that improve this O tilde n to n to the 0.9 approximation. Okay, even if it's still like a quite large polynomial, it's already very hard. And more recently, by a sequence of other 2 breakthrough papers by Kobayashi and Theopoulos, they improve this further to square root of n approximation. Okay, and the latest one is just stop 2019. Okay, and today I'm going to present 2 results on this. Combined together, they gave a subpolynomial, basically n to the list of 1 approximation of this problem. So further improve this n to square root of n to subpolynomial. And the first result is 2020 by Chuzhui, Kobayashi, and me, and second is by Chuzhui and me. The first result is that we just push this a little down for a little just in the exponent. So we improve the square root of n to n to the 0.488 approximation. More important message that I think this work conveys is that it paves a way towards much better approximation. By that I mean all the previous results, so this n to the 0.9 into the 0.5, they use the same algorithmic framework. Okay, but there is an example that shows that this framework just cannot get better than square root of n approximation. Okay, and what we did in this work is that we propose a different framework, a modified one that gets around this barrier. And what we can get is n to the 0.488. This is a modest improvement in the approximation ratio, but message is it can get around some barrier of the previous framework. Okay, so this is our first work. And actually using this framework, we managed to reduce the crossing number problem to a related one called crossing number with rotation system. We will go to this problem's definition very soon. Okay, but this is the first work. Get around the barrier, reduce it to another problem. Along the way, improve the approximation ratio by a little. The second work is that we eventually managed to design a subpolynomial approximation for this new problem. Okay, subpolynomial approximation algorithm, which is n to the little 1, which has actually 2 to the log n to the 7/8. And eventually combined with the first result, basically the reduction part, this gives a n to the little 1 approximation for the crossing number problem of bounded degree graph. Okay, so this is the result that I'm going to cover today. The remaining of this talk is divided into 2 parts. In the first part, I'm talking about this reduction thing. The second part, I'm talking about how to achieve this subpolynomial algorithm. Okay, and yeah, at this point, is there any question for the results? Okay, so before we dive into part 1, part 2, let's first look at what this new problem is. Okay. So it's called crossing number with rotation system. Okay. It's a very similar problem. The input is a graph G, but apart from that, we're also given for every vertex a circular ordering on its incident edges. Okay, so for example, if we are given a graph with 6 vertices and V1 is incident to 4 edges, then we are additionally given an ordering on these 4 edges. Sorry. And the goal is to compute the drawing of this graph that respect all the circular orderings. So basically, if we are given like 1, 2, 3, 4, this ordering around V1, then the drawing we compute, these 4 edges must enter V1 in this order. Okay. It looks like we are given more requirements of this. Okay, so this is both a advantage, but also a curse. Advantage means we basically know what should this edges enter this, but the curse means we have to sort of respect it. But it comes both ways basically. Okay, so is this problem definition clear? We will be reducing the general problem to this problem and then solve this problem in 2 steps. Okay, so let's get into the first part. Okay, it's to reduce the whole problem to this problem. Okay, so let's look at how the previous algorithm solved this problem. They all follow this very simple framework, and that's also the framework that's used in a lot of heuristics, and also whatever is used in the practical algorithm, as far as I know, is also this framework. Okay, so this very simple framework, it consists of 3 steps. In the first step, we compute a planarizing edge set E prime. Here, a planarizing edge set is just a set of edges whose removal leaves the remaining graph a planar one. Okay, so like what we are doing here, for every crossing, we take out one edge, and what we are getting is a planarizing edge set because the remaining graph is planar. Okay, so this is the first step. The second step is compute a drawing, a planar drawing of the remaining graph, because we do know that it's already planar one. Right? We can compute a planar drawing of it, and that's what we do. We draw it in a planar way. The third step is add the deleted edges back. In this way, we just obtain a drawing of the result graph. Okay, so for example, if the graph is K5, we do know it's not a planar one. Right? And deleting any edge will give us a planar subgraph. Okay, and this is a drawing of K5 minus one edge in a planar way. Okay, and the last step is we add this missing edge back, okay, which will cause one crossing in this drawing. Okay, so this is basically one way to implement this framework on a very simple example. Okay, so how do previous works use this framework? Let's look at each of these steps in detail. Okay, so first, the first step is to compute a planarizing edge set. And it is not hard to observe that there exists a planarizing edge set of size CRG. It is just what we have done here. Okay, look at this optimal drawing. And for every crossing, we take out one of the edges that participate in it. Okay, so we basically collect a set of edges, and we are guaranteed that removing them leave the remaining graph a planar one. Okay, so this is what we have just done here. So there exists a planarizing edge set of size CRG, and this CRG is sort of the best quantitative bound we can hope, because it can be just the graph is a copy. It's a union of a lot of copies of K5. So crossing number is how many copies, and how many edges you have to delete one from each copy. Right? So this CRG is basically the best quantitative bound we can get. And basically in the breakthrough of two papers by Kobayashi and Zihan, they gave a polylog approximation algorithm for finding the smallest planarizing edge set. This is a very cool result, and that leads to the square root of n breakthrough eventually. So combine these two results. What we can show is we can efficiently find a planarizing edge set with size approximately CRG. Okay, so I'm not going into the detail of this two papers by Kobayashi and Zihan. It's sort of in a different fashion, but just combining them, what we can say is this. Okay, and in the previous work by Theorem and Zihan, they showed that given anything that we get out of this first step, okay, so given any edge planarizing set, we can implement the third and the second and the third step in order to compute a drawing with approximately E prime times CRG plus E prime crossings. This is what they have shown. Okay, so combined with this yellow box, this is CRG and this is CRG. So this is CRG square crossing. So what we can get out of this is we can compute a drawing with CRG square crossing. Okay, so all these are previous results, but this is what we can get out of it. And recall that we do have a n plus CRG crossing algorithm. And combined with this CRG square, this is what we get, square root of n approximation. So when CRG is larger than square root of n, the n plus CRG is better than square root of n. If CRG is lower than square root of n, then CRG square is better than square root of n. This is how they get square root of n approximation. Okay. Okay. So now I'm going to show a barrier that this framework, the best they can get is just a square root of n. Okay. So what is shown in the previous work is, no, it's not the previous work though, but it's what is shown. There's an examples that for every k, there's a graph with crossing number k and a planarizing edge set E prime with just k edges, such that any drawing of the graph that draws the remaining graph in a planar way has to contain at least k square crossings. So this is basically showing that this k square is just CRG square is tight. Okay, I'm going to show what this example looks like. Can I use the board over there?
Yeah.
Okay. It's a very simple board. It can also be found in one of the appendix of our papers. Okay. So the graph looks like this. the edges. Okay, of it. Okay, so this is graph. With this, I'm drawing the optimal drawing of this graph. Okay, so because it's hard to specify a graph without drawing it, but any drawing will consist some crossings. This is the optimal drawing. So what are the vertices? It has a sort of square boundary of its, like that contains 3 on the top, 3 on the bottom, and let's say 1, 2, let's say 10 on the left. Or actually, it is 2k on the left. Okay, there's a k here, and 2k on the right. Okay, and another like straight line that crosses this square that contains k vertices on the middle. Okay, so we can sort of think of this as the vertices are grouped into groups of size 5. Okay, this is a group of size 5, 2 on the left, 2 on the right, and 1 in the middle. Okay, and this is sort of copied throughout the square. Okay, so this is one group, another group, sort of independently in the graph structure. Okay, so between these 5 vertices, the left top is connected to the middle one. The middle one is connected to the right bottom. And the left bottom is connected to the right top. 3 edges, just 3 edges. Okay, so this is one edge. This is one edge. This is 2 edges. This is edge 2, this is edge 3. Okay. So 1 and 2 are just a short one. And number 3 are the long one. And it is the number 3 that causes crossings. Okay, so in this drawing, there are 1 crossing for each group. So it is basically k crossings. Okay. So basically, the number of groups here is k. Okay. And also, there are other edges, which is this orange edges. Okay. Orange edges are just starting from somewhere on the top and connecting them to the somewhere in the bottom in some certain order. Okay, and there are k of them on the left and k of them on the right. Okay, so this is a graph, and this is what I'm drawing here is an optimal drawing. It contains k crossings, 1 per group. Okay. Now let's think of these orange edges. All these orange edges are E prime. They are a planarizing edge set, actually. I'm not drawing in this way, but I'm going to draw another one that shows that this is a set of planarizing edge set. So this, all the white part can be drawn in a planar way. So how can we do it? Can we still see this? Yes. How can we draw the remaining graph without all these orange edges in the planar way? This is what we can do. This edge is still here. It's only we take the long edge out of it. Okay, so the first edge is now here. Okay, second edge now here. Third edge. Okay. This is a planar drawing. Okay. We just take the long edge completely out of it, and as they appear on the boundary in a certain order, they do not cause any crossing outside. Okay. And this is the unique drawing of the remaining graph. It is probably not easy to see it directly, but this graph is 3 vertex connected, meaning between every pair of vertex, there are 3 vertex disjoint paths connecting them. And such graphs contain a unique planar drawing. If it is unique, if it's planar, then it contains a unique planar. Okay, so basically we sort of want to add something in the middle. It's basically make it 3 connected. In fact, this is not very important. We just need this crossing. The essence is they cross inside, and if we put it outside, it may just not cross. The goal that we put this like middle line in between is to make it 3 vertex connected so that the graph is planar and has a unique planar drawing. So this is the unique way to draw it. In this case, no matter how we draw the remaining edge, it has to incur a lot of crossing. Okay, so if we go outside, you have to incur like k crossings. If we go inside, it has to incur k crossings as well. So basically in the unit planar drawing, this has distance, like edge, face, distance, k for every pair. This is an example. Okay, is there any question about this? Yeah.
You have an existential, you have a graph, and then there is this planarizing set, but is it possible to get for all planarizing sets?
Yeah, so they exist. And what we are going to do is basically modify the framework a little bit like what you are saying. We do not just take this bad, but we want to do something else so that the remaining graph satisfies some properties and this no longer holds. This is what we are going to do. Yeah, so this is not for us, they exist.
Okay.
Okay. Yeah, so basically if you in this graph, you take not only all the orange edges, but also these long edges, then the remaining graph is still a planar. And they can be drawn just in a almost optimal way. Right? So if you take more edges, make it a bigger one, yeah, this no longer holds. Okay, so what we are going to do is we propose a modified framework that gets around this barrier. Okay, so it's basically as you said, it's not for all planarizing set, and this is the advantage that we're going to take. So you give me a bad set, I'm not going to take it. I'm going to put more edges into it so that the remaining graph, I do know how to draw it essentially, and then add this edge back. So it contains 4 steps. The first step is just identical to the previous one. Actually, we will be just using the previous algorithm for computing the approximately the best planarizing edge set. Okay, but after that, we allow ourselves to augment this set to a bigger set called E double prime, such that its size is still CRG approximately, so it does not basically blow up in size. Okay, but the remaining graph has some additional properties. Okay. This is basically the only modification of the framework. Okay, and the third and fourth step is identical to the previous second and third steps. It's compute the drawing of the remaining graph in a planar way. Still, we have to do it in a planar way and add the edges back into the drawing. This is our new framework, modified one. The first question is basically, does this even make a difference? Does this new additional step? And what we prove in the first work is that it does. Okay, the main theorem is we can basically, given a planarizing set, augment it into a set E double prime, such that there exists a near optimal drawing in which only this planarizing edge set participates in crossing. Okay, there are 2 things to pay attention to. First, there exists a drawing with approximately CRG crossings. This is what we mean by get around this CRG square barrier. Okay, it's possible that if you just take this set, the best thing you can do is CRG square crossings. And now CRG is what we get around it. And also a small thing, there exists a drawing. We cannot find it at this moment, because if we can find it, we just directly get a polynomial approximation for the whole problem. Okay. So yeah, it gets around this barrier, but still needs to do something else to find it. Okay. And another point to pay attention is only edges of E double prime participate in crossings. Okay. So originally, what is required? We take out a set of edges, draw the remaining graph in a planar way, and add these edges back. Which means every crossing involves at least one edge in the deleted set. Okay. Because it cannot be a crossing just contain 2 edges in the remaining graph. The remaining graph is drawn in a planar way. So every crossing involves at least one edge in E prime. Now, what we are requiring here is every crossing involves only edges of E double prime. So 2 edges of E double prime. Okay. So basically, the remaining graph, not only are they drawn in a planar way, but they also just cannot cross with any new edges that we eventually added to the graph. Okay. So it's a stronger requirement than the remaining graph drawn in a planar way. Okay, so these are the first main results. And this is basically the reduction part. Okay. And what we show next is if we can get this, then implementing the remaining third and fourth step is actually equivalent to solving an instance of crossing number of this rotation system. Okay. And this is what we mean by this is reducing the problem to a rotation system. Okay. So in the first paper, we gave a slightly better than non-trivial algorithm for this one, thereby improving square root of n to n to the 0.488. Okay. So here, with this framework, just any trivial algorithm for this one already gives square root of n. But a little bit improvement on this gives a little bit improvement on square root of n. And the second work, we just improve this furthermore significantly. Okay. But for the first part, let's just focus on this main theorem. I'm going to show some ideas improving it. Okay. So let's recall what the main theorem says. So there's an algorithm that given a graph and an edge planarizing set, we can augment it into a bigger one, but size is still approximately CRG, okay, such that there exists crossing. But there exists a join that approximates the optimal, such that only edges of E double prime participate in crossings. Okay, this is what the main theorem says. Okay, so actually, why this main theorem is So how we are going to prove it? We are going to basically focus on the remaining graph, and until it gets some good properties, we will stop and say that okay, the edges we are taking out is the set where that is the set we want. So some intuition, what we are going to do is that from previous work has been shown that if the graph satisfies these good properties, then there is a near optimal join in which edges of these clusters do not participate in crossings. Okay. So if a graph is just contains a set of disjoint clusters that are satisfies these three properties, then there exists a near optimal join in which these edges do not participate in crossing. This is what we require actually. These edges do not participate in any crossing, even with the new ones. Okay. Okay. So this is sort of intuition of what we're going to do to the main theorem. There are two things to do in the first step. First, why this intuition is true. Second, how we use this intuition to prove the main theorem. Okay. So first, the question. Okay. Yeah. So let's maybe look at what are these good properties that we want. Okay. So these are three properties: three vertex connectivity, strong planarity, and bounded well linkedness. Okay. Let me explain them, each of them. So three vertex connectivity is just the graph is three vertex connected. It's just what is required for a planar graph to be having a unique join. So between every pair of vertex, there are three node disjoint paths connecting them. Okay. So for example, in this example, like this pair of vertex 1, 2, 3, okay. Vertex disjoint except for the endpoints. Okay. And this is true for every pair of vertex in the graph. You can check it. So three vertex connectivity and also strong planarity. Strong planarity means the cluster is a planar one, and as it is a three vertex connected planar one, it has a unique planar join. Okay, and the strong planarity requires that in this unique planar join, there are some vertices that connect to the remaining graph. Okay, so recall that G contains a lot of clusters. This cluster do not form all G. There are other edges. Okay, the vertices in this cluster that are the endpoints of these other edges, the blue edges, are called boundary vertices of this cluster. And in a strong planarity, it is required that all these boundary vertices appear on the same face of the unique plane join. Okay, so for example, in this green part is a strong planar cluster, and this is its unique planar join. These are the three boundary vertices because these are the three vertices that connects to the intercluster edges. We require all these three orange ones to be on the same face of the planar. Okay, this is just something additional. Okay, has a unique planar join, but all now has to be the same face. This is basically in order for the remaining graph to be in a comfortable position with this one. As long as we find the join of this cluster, we can contract it to the single vertex and worry about the remaining graph. Okay, so just lies on just one face of it. And then boundary well likeness. Still, it's about these boundary vertices, orange ones. Well likeness is some property that is used a lot in the graph routing problems. And here it is just saying it is sort of very well connected inside it. I'm going to present the definition later, I mean, in the second part. This is not very important for us at the moment. This sort of very well connected here. So maybe let's look at an example here. In this graph, the boundary vertices is all these orange ones, the endpoints of the orange ones. They are half of them lying on the top part, half of them lying on the bottom part, and they're not well connected together. Because from the bottom to top, there are just the three paths, right? But there are k vertices waiting to be connected. There are only three railways. Okay. And what we mean by boundary well likeness is they can sort of connect however they like with low congestion. Here, if they want to connect K to K, then it causes a lot of congestion. This is why this is bad and why we want this boundary likeness. Okay, so why this intuition is true? So let's just try to see. We're going to show basically some pictorial explanation of this intuition. So if the graph contains a lot of these clusters, then there exists a near optimal drawing in which all these clusters are drawn in a planar way, and it can be sort of massaged such that all these edges do not participate in any crossing. So we're going to massage some optimal drawing in order to achieve these properties. So let's say green part is a cluster. Okay. The blue edges are its intercluster edges. So the edges are connecting it to the outside world. And the red part is the remaining graph. Okay. And let's say this is some optimal drawing of the graph. We're going to modify it into another drawing in which these blue edges do not participate in a crossing. And the crossing number does not increase by a lot, by too much. Okay. How are we going to do it? Okay, so again, this green part is a cluster we're going to deal with. Okay, so first thing is recall that this A, B, the boundary vertices, they're well connected sort of inside this cluster. What we're going to do first is to compute a set of passes that connect A and B to some vertex inside the cluster. This is sort of guaranteed by the well likeness. We can route all vertices to some single vertex with low condition passes. This is what we mean by very well connected. Okay, so like that, this K on the top, K on the bottom, you cannot do this. Okay, have to cause a lot of condition. So first thing, we find this set of passes. Okay, and then we erase the whole green part from the graph. Okay, only this passes are what remains and we're going to use. Okay, and these passes, recall they connect the boundary vertices to some vertex inside, right? So they are originating at A and B and eventually ends at C, somewhere C. Okay, so now we redraw these boundary edges by starting with their original image and extend them along the path we have just selected, so that eventually they all end at C. Okay, so eventually they starting with A and B, and now we extend them along the path we find, they eventually end at C. And then we place a small disk around C. Okay, we put the whole drawing of this green part into this small disk. Okay, the green part has a unique planar drawing with all boundary vertices appear on the same face. And this is the drawing we're going to take and put it in. Okay, all vertices on the boundary appear on the same face, and we just turn them as the ultra face. So we want to expose them. And the last step is we connect these blue segments we see in this disk to the corresponding new AB. Okay, this is how we massage it. Okay, delete from the graph, extend the line, place a new disk, place the drawing inside the disk, and reroute the boundary edges. This is the whole thing. Okay, now you can see that the green part is drawn inside a small disk. And this small disk is sort of disjoint from the whole drawing. And now we get a drawing in which these blue edges are just isolated. They are drawn individually, separately in the planar way and do not just interfere with anything else. Okay, the whole thing, the main thing is finding these passes and extend them sort of along it. And in this step, the fact that these boundary vertices are well linked guarantees that this path has low congestion, which guarantees that the whole process does not increase the number of crossings by a lot. So congestion basically directly means how much you will increase the crossing by. Okay, so for example, if there's one crossing that caused by this two edge, and you use this edge A times, use this edge B times, this crossing may eventually give birth to A times B crossing like that. And low congestion just means that, okay, it's okay. You just do not blow up by a lot. Okay, so the whole proof that this crossing does not go a lot by too much. I'm not going into the detail of that, but the idea is just low congestion, and which originates from the well-linkness, boundary well-linkness. Okay, and we also see that what is required here for planar, three vertex connected, unique one, and the strong planarity. Right? All the properties why they are required is just shown in this process. Okay, so this is the intuition. And if we just take a further look at what is inside the disk, it is on the right, as you can imagine. Okay, so now what we're going to do is to use this intuition to prove the main theorem. What we are going to do is this. We start with an edge planarizing set. We're going to view that these edges are already deleted from the graph, so that the remaining graph it's a planar right, or it's a planar one already. It can be disconnected already, so there are already clusters. Okay, we look at each of these clusters and see whether or not this cluster satisfies these properties. If so, we do not touch it anymore. We just keep it. If not, we will further decompose it by taking another subset from these clusters out into our deleted set. Okay, and the remaining graph may just satisfy better properties. Okay, so it's a whole recursive decomposition process. We look at the clusters that we already at our hands and look at them if they satisfy these properties. If not, further decompose them. If not, further decompose them until all of them satisfy them. We just need to show two things. First thing, we do not in total delete too many edges because we still want these sides to be CRG. And the new sides, the old sides, also all CRG approximately. And same thing, and also we want to achieve these three properties. So basically, we look at them. If not decompose, eventually we want to show you do not additionally delete too many edges so that this thing can achieve. This combined with the property, the previous intuition, just give the first theorem. Okay. This is what we're going to do. Okay, so now let's look at these three properties individually because we want to achieve all of them. Okay, so the first one, maybe the easiest one that we can achieve is boundary well linkedness. So the well linkedness is used a lot in the graph algorithms, and intuitively it is saying the graph looks like an expander. So it's the notion expander here, okay, to all of you. Okay, so expander, basically the whole graph is well connected. And this well linked, the boundary well linked, shows that this boundary vertices are well linked. So they are sort of well linked inside the cluster. The cluster looks like an expander to them. It's just not a global property, it's a local with respect to them properties, well linkedness. And what we can do is just, suppose by hearing about expanders, you also hear expander decompositions, right? So like similar to expander decomposition, here we do well linked decomposition. It's basically finding a small cut along it, and that's it. Basically, there's whole charting argument that chart the number of deleted edges to the smaller sides. Previously, the number of edges, now the number of vertices in the smaller sides. So this is all similar to the expander decomposition, but it is sort of a very mature algorithm that's used a lot in the past 10 years. Well linked decomposition. And this we can guarantee indeed we have not deleted too many more edges. So given every cluster, we can perform a well linked decomposition so that eventually all small clusters are boundary well linked. And the number of edges we deleted is not too many. So this is basically the easiest one that we can achieve. I'm now going to show another one, which is sort of hard and not going into all the details, but just some ideas here. A strong planarity requires that all the boundary vertices appear on the same face of the planar drawing. Right? In this example, the green part is a cluster, and the blue edges are the edges connecting this graph to the outside world. Okay. So what are the orange vertices? Oh, sorry, the orange vertices are just the boundary vertices. And what we require is that they all lie on the same face of the planar drawing, which is not the case here. Okay, so in the planar drawing, there's two face, inner face, outer face, and three on the outer face, three in the inner face. And this is not what we want, so we want to decompose it. In this case, it can be proved that if we want to sort of ensure the strong planarity, what we can do, what we have to basically delete one edge per cycle in order to make them not appear on the same face. And actually the number of cycles can be very many. So this sort of forces us to delete too many edges. And this is something we do not want to do because we want to like not delete too many edges. And number of cycles can be large, so we have no control of it. And this is something bad. And what we get around it is how we get around it is to replace this strong planarity with some weaker property, which is also enough for us to eventually achieve the goal. So what is weaker property? Recall that the strong planarity just give us the freedom of, if we place something inside the disk, then we can reroute things to the boundary. This is all we need for strong planarity. But if we place something inside the disk and the outside world intersected in two faces, for example, outer and inner, we can just reroute the outer part to the outer face vertices, reroute the inner part to the inner face vertices. So we do not really need these 6 vertices lying on the same face. we just need that in the same part that they are connecting with the outside world, they are lying in the same phase. So what do we mean by that? It has a planar drawing in which every pair of boundary vertices that are connected in the remaining world has to lie on the same phase. Okay? So if the whole graph is just an x, y green part connecting by these blue edges, then the x, y and y are not connected to each other. So we do not need to sort of enforce all of them to lie on the same phase, then connect them sort of in a unified way. They can, x can be connected inside, y can be connected outside. Okay. Yeah, so this is still the previous picture. So we put everything inside. Now it's not a disk now, it's an annulus. So something can be connected outside, something can be connected inside. So this is the weaker property that we can still go through with the whole intuition, but it's better for us because we can indeed achieve this. So in this case, we basically don't need to do anything because it already satisfies. The three orange vertices in the inside, they are already like on the same phase. Three vertices on the outside, they are already. Okay. But what if, in this case, there's still an edge connecting to x to y? In this case, we have to do something because they are connected in the whole remaining graph, right? So in this case, we try to still want to achieve that all these orange vertices appear on the same side. And what we do is exactly just deleting one edge per cycle. But now this time, we can afford to do so because we can show that in this structure, no matter how it is drawn, at least it creates number of cycle crossings. This is something we can show. Okay, it's another sort of part of technical things, but I'm not going into the detail. But basically, the green part, as long as something is three vertices connected, is very restrict. And in this case, in which you want to connect the interface to the outer face, the rigid planar part just have to force you to pay a lot. Here it is basically, however you draw it, it has to be number of cycle crossings. And in this case, we are basically can afford to delete one edge per cycle. So yeah, the main idea I want to illustrate is, in this case, we cannot achieve the strong property, the strong planarity property, but we replace it with a break property. And luckily, we can still go with this to use the intuition to group means here. Okay, and actually the combination of the second and third property is already trickier to achieve because by doing well-linked decomposition, you basically decompose the graph, and then the graph may not satisfy the break property because you create new boundary vertices and you do not know where they lie in the planar drawing. Okay, so you may just destroy the break property, and for guaranteeing the break property, you may want to delete a few other edges, like here, one edge per cycle. So you may create like components that are not well linked anymore. So want to do back and forth thing. So combining these two are already very tricky, and eventually it can be achieved. Okay, I'm not going into the detail of that. There are no very new ideas. It's basically charging here, charging there, charging back and forth, and they can be achieved together. So the first thing, it's also very tricky. So eventually we cannot achieve three vertex connectivity, and we replace it with something weaker, but still likewise enough for us to get around the whole main proof. So we do not require the graph to be three connected, but we require something to be two connected. The number of two connected components is small, the number of two separators is small, and we can properly add a few fake edges to make it three connected. So three connected is basically showing that the graph has a unique planar drawing. If it is two connected but not three connected, the drawing is not unique, but up to flips. Okay, so for example, if you think this is a subgraph, this is a subgraph, they're connected by two vertices. Then the planar drawing is up to flips. You can flip just respect to these two vertices, the whole thing, like inside. So two vertices connected means it's still it's not unique, but close to unique, just up to flips. But you can do like a lot of flips because there are a lot of two separators. So every separator you can flip. And what we are going to show is we can add a few edges to make it three connected. So basically, the type of flips you can do is sort of limited by us. Okay, the whole thing is not guaranteeing unique planar thing, but we basically still require that we do know how this planar cluster is drawn and how the remaining parts is connected to it, which part in which phase, we still know it. This is basically the intuition. It's just something weaker. Okay, I'm not going into detail of this similarly. So the idea is we sacrifice two properties, but replace them with two weaker ones, and we still manage to get through it. Okay, so this is the proof of domain theorem. Where are we now? So we can now show that we start with a graph, edge planarizing set. We managed to delete a few more edges so that the remaining graph satisfies these properties. What about the properties? The remaining graphs are clusters that are two vertex connected with a lot of property, has bridge property, and will link. Right? What we are guaranteed is that there exists a near optimal drawing in which each of these clusters are drawn in a separate disk. Okay. What we only need to worry about is how these intercluster edges are drawn. Okay. So we do have a lot of knowledge about this near optimal drawing already, so that each part is just drawn inside the disk, and we just need to reroute the boundary edges. Okay. There are no other vertices now; they're just boundary edges. Okay. This is what we're going to eventually add to complete the crossing. In this case, what we are really dealing with is that we can think of this each green vertices as being contracted to a single point. Now it has a unique planar drawing, so the boundary vertices appear on this boundary face in also unique ordering. And the edges that incident to them, they now has to enter this vertex in a certain order. And that is what we're going to force us to do, because we do know that there exists a near optimal drawing that are done in this way. Okay. So now what are the remaining tasks? We think of them as contracting to a single vertex and want to add the remaining edges back. Now these edges have to satisfy circular ordering because of the unique planar drawing. It's contracted, so this have to be in some order. Otherwise, they will create a lot of crossings inside the disk. We do not want to see that. And this is eventually a crossing number with rotation system problem. Okay, and this is like this is something we want to find. Okay, just want to connect them around this disk. Okay, so this is the first part. At this point, is any question? Do we only have a break like that?
We can have a 5 minutes break.
Okay, yeah, sounds good.
Actually, I forgot why we actually need the unique planar
Why do we need the
uniqueness.
Why do we need the unique planar drawing? So this unique planar drawing are needed in order to show that in this picture, in this picture, no matter how you draw it, they incur a lot of crossings. Yeah. So it's sort of already rigid, and anything you've done it causes a lot of trouble.
Yes. So in your so during the presentation, it's actually not
clear. Okay, it's okay.
Okay, right.
Yeah. Okay, so I think maybe I said one sentence, but it's not highlighted here. Yeah, so strong planarity is required.
Time is up.
So what is the thing that you solved or didn't solve?
I told you yesterday.
Yes. But you said this morning that you have something that you which is new.
That's a nice idea, which we're trying to figure out whether it's new or not. But, I mean, I can tell you that you can also tell me. So you remember the problem? Equivalent to saying to each, so you have to each vertex you assign a binary vector where the length is the number of colors. Then for each hyperedge of color I, you have sum of the three corresponding three verses, you sum up their labels. You should get ith curve.
Wait, what? So you're saying this is equivalent to the problem from yesterday?
Whether you can find.
But I never know that. It's also interesting. Yes, I should.
What?
So in the first half, we basically reduced the crossing number to this crossing number with rotation system problem over here. And then the second part, I'm going to show you n to the list of 1 approximation for this problem. And yeah, the whole algorithm is very complicated. So still, basically, framework is what all I'm going to show, and hopefully it makes some sense here. So let's look at this problem again. Okay, the input is a graph. And in addition to that, we're also given for every vertex the circular ordering on all its incident edges. Okay. So basically, when we want to compute a drawing, the incident edges entering this vertex must obey this order. Okay. So there are small technicalities here. So although a circular ordering is given, its flip status can be chosen by us. Okay. So we're only given 1, 2, 3, 4, but it also can be 4, 3, 2, 1. Okay. So this is okay. And also, as the graph has a unique planar drawing, right? The green part has a unique planar drawing. It's also unique up to flips. Okay, so the boundary edges can enter here, but if we choose it this way, then enter in the different. Okay, we can choose this. But they're just a small technicalities. And we want to compute a drawing that respects all these orderings, but up to flips with fewest crossings. Okay, so that's a problem. And there are some works on this previous one. Yeah, on this crossing number with rotation system one. So previous work in cubic graphs, where the graphs are having max degree and most 3. Okay. This problem is just equivalent to the crossing number problem, because if we imposing a ordering on 3 things and still allowing the flip, it's basically imposing nothing, imposing no constraint. The 3 things still up to flip. Okay. So in cubic graph, this is just equivalent to the crossing number problem, and the strongest hardness result also apply for cubic graph. It's still only APX hard. Okay, and the only previous approximation algorithm for this problem is n to the 4 approximation. So this may seem to a little weird. Previous ON now into the 4. Now, in this problem, the input can be a multigraph now. But it has to be a multigraph because it obtained from the original graph by contracting each parts into a single vertex. So there just can be a lot of edges connecting different parts. Only they are like the orderings are different. So this is what we need to like conquer. Okay. So n to the 4 is still non-trivial because the number of edges can be like significantly larger than the number of vertices. So that's still non-trivial. And in this case, so even with the flip status is fixed, we can also achieve n to the 4. This is the only previous work on this problem. Okay, so what we are going to show is we can achieve like OPT plus EG times n to the 1. Okay, so we can find the drawing with this many crossings. OPT is the optimal like number of crossings like respect this rotation system. But we now allow ourselves to compare with the number of edges. Okay. So there n to the 4 is n to the 4 times OPT. Ours are n to the little 1 times OPT plus EG. We can do so, we like dare to do so, because what is EG? EG is a set of augment set. It's an augment set. It's the blue edges, whose size is approximately CRG of the very original G. Okay, so we're given a planarizing set, we augment it to obtain a lot of blue edges. So EG is still CRG. So this OPT is CRG, EG is CRG. We're comparing with both of them. It's okay. So just problem-wise, this is not compared with this one. But in order for a general goal, this is okay. Okay, so this is what we're going to show. So recall just the one thing to remember here is we compare ourselves with OPT, but also EG. So the whole framework is the divide and conquer algorithm. We're going to divide the input graph into subgraphs, subinstances, and smaller instances until the instances are small enough so we can like achieve some just apply some trivial algorithm to compute this optimal way. Okay, so this is top-down divide step and bottom-up compose step. So in order to like for this framework to work, we have to be able to perform this divide step. And also for each small enough subgraph, we will apply some trivial algorithm to compute this optimal drawing. And we are going to compose all these drawings into a drawing of the instance that give birth to them. Okay, so we need to be able to do both top-down divide and bottom-up compose steps. In order for this framework to work out, 3 things need to be satisfied. Okay, the first thing, when we care about just one step of divide, dividing G1 into G2, G3, G1, G2, G3, 3 subinstances, the optimal solution, sum of OPTs, cannot be too much larger than the original one. Right? We want to like divide, and the number of steps will be something like log n. Okay, we do not want them to blow up by a lot. Okay, so smaller than equal to is just some small constant. Okay, and by the way, depth is not log n. It will be some complicated small term, smaller than log n. Log to the, but not going into the detail of that. But the idea is, in every step of divide, the sum of OPT cannot be too much larger. And also, since we are comparing to both number of edges and OPT, the sum of number of edges cannot be much larger. Because eventually we're solving, comparing ourselves with OPT plus EG. And also there needs to be a composing algorithm that given for all these subinstances, a drawing of them, compose them into a drawing of G. So basically this whole thing like need to work out as long as we satisfy these 3 conditions. Okay. So does this make sense? We're going to look at each of these 3 conditions in turn. So we haven't specified how we perform the divide step, but divide basically subject to like, these goals. We have to make them satisfy that this can be achieved. Okay, so let's look at the most natural or most simple way of decomposing a graph into subinstances. What you can do is this, just find the cut. And these are the edges that cross the cut. Okay. We remove them, and what we get is 2 subgraphs, G1 and G2. Okay. This is the most like simple way of decomposing a graph. So it can be seen that the number of edges, right, EG1 plus EG2 is less than EG, right? Because they are just partitioning the original set of edges, and we still delete some edges of it. Okay, and CRP1 plus CRP2 is less than CRG. because if we take the optimal drawing of G and we just look at the G1 part, look at the G2 part, like the number of crossing in it sum is less than CRG. But the thing is, we cannot, in this case, simply compose the two drawings together. Okay, so basically the first and second properties are good, the third one is problematic. Why is that? If this is a drawing of G1, this is a drawing of G2, we do not know what it is actually. It is based on recursion and basically the top down and bottom up. We get some drawing of G1, some drawing of G2. We have no control on it. And now we're going to produce a drawing of G. Okay. And basically what we can do is add the missing edges back, add this orange edge back. Okay. But one edge here may create basically a curve like this that cause a lot of congestion, a lot of crossings. So in the worst case, it may cause crossings with most edges in the current graph. Okay. So in this case, so in this case, it's it's too many crossings for us. Number of cut edge times EG. This is this is just too much. It's like the factor we lost. This cannot be tolerated. So what we do is we have to do something to the device step. We cannot just take G1 and G2 and recurse. We need to add some structure to it so that this composing step can be done. What is the structure? It's also very simple. We add for G1 a special node, which is denoted by the red circle, and add an edge that connects all the cut edge endpoints on the left to this new special node. Okay, so basically, instead of taking just the G1 and recurse, we add something to it. And this is the instance we're going to recurse. Okay, and we do the same thing for G2. Okay, so EG, yeah, we are adding these edges. As long as these edges are not too many, EG, number of edges in the new instances are still okay. So we are adding this cut edges, but we basically need the cuts to be somewhat sparse. Okay, and OPT, we need to discuss that. Okay, so it's not immediately clear that OPT G1 plus OPT G2 is still less than G because we have added something to it, right? We need to use. But now I'm claiming first that CR, so the composing algorithm can be done. So given a drawing of G1, given a drawing of G2, we can now compose them into a G. How is this done? It's something similar to the curves inside of disk thing. Let's say if we have a G1 drawing on the left, a G2 drawing on the right, okay, we look at basically there's two special vertices. Okay, we start with drawing of G1 and look at the image of the special vertex, the red one. Place a disk around it. Okay, now I'm drawing it very big, but in fact, what we're doing is place a very small disk around this image. Okay, we put the whole drawing of G2 inside it, but we need to be a little bit careful. Okay, so this is a drawing of G2. We carve out a small disk here and view things inside as the outer face of this drawing. This is the drawing that we put into the small disk. So what we put into small disk is something like this. So when we carve out the small disk around the special vertex in G2, all these purple curves touch the boundary of the outer face. And this is what we want. And so now they do not like contract to a single red vertex, but now touch the boundary. Okay. And now the same thing happens again. We see in this annulus, we connect it. Okay. And the whole like the purple parts can be connected within this annulus so that now becomes the cut edge. Okay. So the special vertices do not participate in the original graph, but they are there in order to help us to compose the drawing. Eventually in this drawing, there are no special vertices. They're just like throughout cut edges connecting. Okay. So as you can see, there are still like possible crossings happening in this annulus, right? So basically, the composing algorithm, we still might just suffer some additional loss. So one technical part is recall that the instance that we are recursing on, there's still instance of crossing number with rotation system. Right? So we have the freedom of defining what is the rotation system here. What is the rotation system here in the sub instances? We can do it in a very delicate way, such that either all this like reconnecting things happening in the annulus do not create any crossing, or they create some crossing but can be charged to OPTG and create the OPT of this sub instances. This is some very technical part, but I'm not going to. But the idea is, as the instance contains the crossing number as the instance contains the rotation system, we can use this power to basically design the instance input in order to reduce its cost. Okay. So basically what we are doing, the trivial G1 and G2 separation thing does not work for composing. We add something to it, add some complication to the instance. Now composing works. Still with a lot of effort because we want to define the rotation system in a very adaptive way. But now the OPT is not clear. The number of edges is still clear as long as the cut is relatively sparse. Okay. So now we are sort of satisfying the third condition, but not the first one. And we want to sort of do it in the next step. Okay, so actually what we are doing is not cutting the graph into two, but cutting the graph into simultaneously a lot of components. Okay, so we're not just creating two instances in a step. What we are creating is a lot of instances at the same time and recurse all of them in the same time. Okay, but for every, basically we decompose the graph into clusters. And for every cluster, we create another instance, which is called cluster instance. It's basically like still adding the special node and connect all the boundary edges to it. So from this cluster, it's looking like contracting the outside world into a single vertex. This is the new instance that's going to work on. Okay, and in order to connect all these drawings together, we need another central instance. Okay, so if there are just two, then just one special vertex, they are combining at this special vertex. But now there are many clusters. We need to compose them all in an organized way. And that is why some other central instance is needed. Okay. But this is just technicality. All I'm going to say is we do not cut the graph into two, but many simultaneously. And each cluster can be viewed as starting from this cluster, contracting the outside world into a single vertex. And that's the instance we are going to recurse out. Okay, yeah, but recall there is still a problem. Okay, so the composing problem is solved. And the number of edges, as long as the cut is relatively sparse, it's okay. But still, there's OPTC. Why is, in this case, OPT new instance G1 plus new instance G2 less than sort of OPT of G? Okay, originally, G1 is just part of G. G2 is part of G. We look at the drawing, part of G1 is part of G2 drawing. They just naturally set aside this. But now we want to still just extract a drawing of this new G1 and extract a drawing of this new D2 from the original optimal drawing of G. Only thing we need to handle is where we want to place this new vertex and how do we want to draw this additional edges. This is the only thing we want to handle. And we want to ensure that they do not create a lot of additional crossings. Okay. So let's assume that in G2, there are one additional property. Okay. Let's assume for now that all these cut edges, they can be routed to a single vertex in G2. This is all in the graph, this is no drawings. Routing to a single vertex in G2 via passes in the graph. And if there exists a set of edge disjoint paths that routing this boundary edges to this special node, then I'm claiming we can extract a drawing of G1 from the original drawing. How? We look at the original drawing of G. We keep all the left part as the drawing of within this circle. We view the image of this vertex as the image of special vertex. And now we need to draw these edges. How? It is just the combination of this edge's image together with this path's image. Okay. But okay, so yeah, this is sort of a critical part for intuition. So basically, all these paths that we want to find, it seems very complicated, it seems a gigantic structure, but they're only serving the purpose of creating the image of these new edges. And we sort of need they are edge disjoint so that the curves are really separately and reaching eventually a same point. Okay, so this routing to a center is very important because we need a center here for special vertex. Okay, so this sort of requires that we cannot perform the cut arbitrarily. We want to cut the graph into clusters with this type of property, and then we are good. Okay. So actually, this edge disjoint paths, they do not necessarily need to be edge disjoint. Again, they can be causing low congestion. They can use same edge. It's only just when we create the drawing, we do not really want the curves to be overlapping. We just slice it, nudge it a little so that they are like sort of deviating. But basically, low congestion ensures that we still use the original optimal join, and the number of optimal join in these two joins we create are not too many, not too larger. So edge disjoint is ideal, but low congestion is still enough. Okay. The idea on this slide is we want paths in G to create new edges images, and actually low congestion routing in G just give us cheap drawings for G1 and G2. Okay, so basically this is one properties that we want for this cluster. Okay. We want to cut the graph into clusters. How? Graph clusters with this property. It's a routing to a center property. Okay. So the boundary edges can be routed to a center. We do not actually know this property well. We're not quite familiar with this routing to a center, but we are familiar with another one, boundary well likeness. Boundary well likeness is saying these edges can be routed to a center, edges can be routed all to all via some low congestion, more commodity flow paths. Okay, so this routing to a center implies route all to all, because if you can route to a center first, then by splitting the flow evenly, you can route all to all. This is all intuition. This is all like more commodity flow arguments. I'm not going to like explain into detail. But routing to a center is a strong property that is stronger than route all to all. And routing all to all is what we know as sort of well likeness. Okay, now let's look at the well likeness here. So a cluster together with these boundary edges are called well linked, or bandwidth property, or boundary well linked. Okay, there are different names. If for every partition of the cluster into two, the number of edges crossing them is comparable with the number of boundary edges on the smaller side. Okay, so here, 4 edges here, 3 edges here. This cut have to be comparable with 3. Okay, this is what basically like a well likeness is. The well likeness saying that we can send all to all, right? And if you want to send from this 4 to this 3, you have to basically send 3 units of flow. And this is saying that the cut is not smaller than 3. So it stops like from this cut forbidding you to send auto flow. Okay? And as the flow cut gap is small, so flow cut, ST flow equals ST cut. It's max flow mean cut theorem. Multi-commodity flow, there's a gap, but it can be proved that gap is small, polylog, normally log. So here, cut condition just gives you flow, like the availability. So as long as all cut are good, you can send the flow via low condition. This is basically the flow cut multi-commodity flow result, and that's why the condition, sort of cut type condition, is used in a lot of graph algorithms. So this is routing all to all. Or in other words, that's a well linked. This we do. We do know how to decompose the graph into well linked clusters or boundary well linked clusters. But is the inverse, is the converse also true? So we do know routing to a center imply well linkness, but well linkness does not necessarily imply routing to a center. Especially here, we are requiring something stronger. Okay, the second technical part of this work is to show that in general, this backward direction is not necessarily true, but in our purpose, it is true. So we do not really need routing to a center on the surface. We only need well linkness, but only in our problem setting. Okay, what do we mean by that? If a cluster is well linked, either we can find a random routing to a center. Okay, this has to be a random set of passes that cause expectation of congestion squared of each single edge bounded by a subpolynomial factor. Or we can certify that something else is happening. This is some problem, but it's sort of a good thing in our case. What is this problem? OPTC plus EGC is larger than the boundary edges squared over until 1. So delta C is boundary edges squared. Okay. Intuitively, what this means is that the trouble created by this cluster can be charged to itself. What is the trouble created by this clusters? Boundary C squared. Okay. If we just cut this and separately do 2 drawings and combine them, the maximum number of crossings that we create in the middle is this boundary edges. This boundary edges, in the worst case, we can just allow them, each pair of them, to cross once. Okay. If we cross twice, we can always uncross them. So we can ensure they cross pairwise and most once. And in total, this is the trouble they cause. Boundary edges squared. Okay. Now they are less than OPTC plus EC. Okay. So basically, you will create some trouble, but it will be part of your original cost you have to pay. And we can just recurse on them. That's so enough. Okay, so in general, if we like ignore this condition, then the result is not correct. Okay, but luckily we can find a sort of another condition here, and that is good for us. So in this case, we can basically cut and recurse down to subgraphs. We do not even need to sort of special words. It's basically saying the trouble created by a parser can be charged to yourself, and we can still just carry on with the recursion. So there are two small comments I want to make here. So if we want to get expectation congestion of a single edge, then it is easy to get, if we do not allow expectation, we just want to ensure that congestion is bounded by some polynomial. It's impossible. Because think of a grid. So let's say K by K grid. The boundary is well linked. Sort of on the boundary of grid, you can route however you want, right? But the grid is a bounded degree graph. So it's a degree 4 graph. Right? So if you want to route like the first row to some point, some edge has to incur a lot of congestion. Right? There are 100 vertices you want to route to a single point, and that single point only has degree 4. So some edge will cause a lot of congestion. So if we just want congestion to be bounded, it's impossible. We have to do this randomizing. So expectation of congestion. If we want expectation of congestion, we can get polylog n, but that is not enough. So expectation of congestion, that's polylog n. This is just guaranteed by well linkness. So it's like well link can send all to all, right? And you randomly pick one of them, and you do not send all to all, but just send to one of them. And this will cause polylog n. And this is sort of in the very first step. Recall that we are finding passes from A and B to some C in the center. There we only guarantee expected congestion. We do not guarantee expected congestion square. Okay, so that is only like boundary well linked is enough. Okay, so idea is if we just have congestion here, it's easy, but we want something stronger. For something stronger, the intuition is still if we A edges take this edge, B edges take this edge, then this might eventually give birth to A times B crossings, and only A square plus B square are enough to bound it. Okay. A plus B is not necessarily comparable with A times B. Okay. And this is why we need congestion square here. Previously, in the whole composing, in the previous sequence of pictures, this is not a problem because we will be eventually uncrossing all these boundary vertices, uncrossing this like boundary passes. I haven't gone into the detail of that, but just so you know that here we need something stronger than that because here the composing is complicated, more complicated than that. So this is another technical part of the paper. I'm not going to, but just introduce what we have proved here. So basically, the idea is well linkness is enough. Only in general, it's not implying routing to a center, but in our case, it is good enough because this other thing is also good for us. Okay. So basically, what we have proved so far is routing to a center equals well linkness property. And what we want to do is, what we can get out of it is that by cutting a graph into smaller parts, we only need them to be well linked clusters. So we do know how to do it. We just do well linked decompositions, and that's it. Okay. Now another technical problem. Recall that we want to bound OPT G1 plus OPT G2. In order to bound OPT new G1, we want this set of passes to exist. We're routing to a center on the right side. We also want to bound OPT G2. So we also need this type of passes. Okay. So OPT G1 plus OPT G2 to be bounded, we need that this path to be routable to a center in G1 and in G2. So in general, we want to sort of find a cut that is routable to a center inside and also routable to a center outside. This is some property that we want. So it's actually even stronger than routing to a center inside. So what we need is routing to inside and outside to a center, to two centers actually. And this is called doubling well linkness. And unluckily, we do have algorithm for well linkness, but we do not have algorithm for doubly well linkness decomposition. So we can decompose along sparse cut, but what we can guarantee is that within this cluster, boundary can route to a center, but not necessarily boundary can route to a center outside the class. So this is another technical part. And eventually, I'm not going into the detail, it's another main technical part of the paper. We say, what we can show is that, okay, well linkness actually is enough. We do not need really this W well linkness to carry out whole plan. But it comes at a cost. Okay, so previously, we do basic disengagement. So cut into the graph into G1 and G2. For G1, contract the outside word into single point. G2, contract the outside word into the single point. This is the two instances we're going to recurse on. This is called basic engagement, basic disengagement. And now we're going to make this procedure much more complicated. So as we have managed to show that these link clusters are enough, the cost is the disengagement procedure has to be much more complicated. So in fact, originally the clusters are for each vertex, look at the outside wall contracting the single vertex. That's what we get. Right? And now what we're going to do is this. The outside wall is probably decomposed into several parts. And we contract each of the parts into a single point. And that is the instance where it is on the right bottom. Okay, so we will be eventually recursing on them instead of just one single word. Okay, so I'm not sure if it is any convincing, but well linkness, the distance from W well linkness can be overcome, but it comes as a cost of creating subinstances. Okay, so let's now assume all this is true. Okay, so we basically know how to create subinstances. It's done by advanced disengagement. And we can show that by doing this carefully, we can bound the OPT sum and the crossing sum. Okay, so it comes at so into the little one of OPT. So this is originally it is here by less than this sum, but now we can we have to sort of allow some slack here. Okay, this is trouble causing by some cluster charge to yourself. See, it all goes to that term. Okay. Yeah. Okay, so let's look at the remaining step. We want to bound the number of edges. On the slide, this is the last step. If we still want more discussion, I can present some N plus DRT, but yeah, this is the last part. They will see. Okay, so in order for this divide and conquer to work out, we still have to make sure another thing is that the number of edges in the subinstances are significantly smaller than the original one. Otherwise, it's possible that every round we do not touch this graph a lot. For example, we're just removing a small part of it, then the depth will just blow up. Okay. We want the depth to be bounded, so every time the size has to be decreased by a significant factor. And this factor cannot be larger than, well, this decrease factor has to be much larger than this one. So we have a blow up when we have a decrease, and this has to be larger than that one in order for whole approximation to be non-trivial at all. Okay, so both of them are into a little one, but one of them is larger than the other. Okay, and this is sort of by more familiar tools. It's by a mean balanced cut. Okay, so a cut is balanced. So basically, if we want to reduce the size on each side, we want the cost to be balanced. Right? If it is balanced, then the size reduced by a constant factor every level, and it's sort of working. And a mean balanced cut, so a balanced cut, maybe for first, is a cut that the remaining components, each of the remaining connected components, is at most like 90% of the original size. 90% is any constant, okay, from half to one, okay, any constant. This is called the balanced cut. And the mean balanced cut is overall balanced cut, the one with minimum number of edges in it. Okay, so mean balanced cut is just this. And what we are going to do is find the mean balanced cut every round. We want it to be balanced, but we do not want to cut a lot of edges. So mean balanced cut is the ideal thing. Okay. And it has been proved by the previous work. This is Leighton and Rolfe, the planar separator theorem. I'm not sure if you heard of it. Okay, the mean balanced cut of a graph is bounded by the square root of OPT plus max degree times number of edges. So this eventually is a planar separator theorem's corollary. But ideal planar separator theorem is you're given a graph of n vertices, you can find the square root of n separator, right? And this is why this square root of n comes into play. OPT is there because our graph is not planar. Our graph has a drawing of CRG crossings. We can sort of view it artificially as planar by putting a vertex at every crossing. So how many vertices are there? N plus CRG. That is square root CRG plus something here. And we do have this max degree term there because we are finding edge cut, not vertex cut. Vertex cut are what are given to us by planar theorem. Okay. This is related to this N plus CRG result. If you are still interested, I can present it later. But what it's saying is, as long as the max degree of the graph is not crazy, and crazy means one vertex take almost all edges. Okay, it's less than EG over into little one. Then either we can guarantee that OPT is approximately CRG EG square, or we can show that balance cut is like less than the number of edges by a factor. Okay, this is just observing this observation from this inequality. Okay, so as long as the max degree is not crazy. Okay, so here crossing number with rotation system, the input graph may not be bounded degree anymore. Okay, in the very beginning we have a bounded degree graph, but now the new instance is obtained by contracting subclusters. So we are given a multi-graph, no longer bounded degree. And this is possible that now it is possible that some vertex takes crazy degree. Okay, and as long as there's no such crazy vertex, we can either say that OPT is at least EG square, or the mean balance cut is small comparable with G. Small comparable with G, we can recurse. So EG1, EG2, their sum do not increase a lot compared with EG. OPT larger than EG square, it means, okay, this is a cluster, we can forget about it. Any drawing is very bad. In any optimal drawing, basically every pair cross, every pair of edges cross. Okay, so we just find some trivial drawing in which we guarantee that every pair of edge cross at most once, and that's optimal already. Okay. So basically, this solves the problem. Number of edges, as long as it is, as long as the max degree is not crazy, it can be done. So what we're going to do is, actually, the mean balance cut is an NP-hard problem. So we can do only the approximate version of it. And luckily, this thing still holds throughout this. So what we're going to do is, we first apply approximate mean balance cut. Like this is a cut we get. We do it repeatedly until the size becomes smaller. It has to be decreased by into a little one, purple into a little one factor. So it has to go deep enough. And then we perform well-linked decomposition, so that all clusters are well linked. And we have shown that we have a way of creating the subinstances so that they can be done in the advanced disengagement way to create subinstance that all these three properties satisfy. Okay, I hope that I convinced you that all this OPT sum, EG sum composing three properties can be satisfied via this process summarized at the end. Okay. However, this deals with a general enough case, but not a complete general case. This deals with a case where there's no crazy vertex. Okay, recall that either or that has a prerequisite, which is the max degree is less than EG over N-1. And in this case, what we have summarized basically all through the second part of the talk is we apply approximate mean cut well-linked decomposition to get small clusters, and we perform advanced disengagement to get subinstances. Okay, this is just divide step. In other words, there's a complete different set of algorithms. Then I'm not going into the detail of any of that, but it's sort of very special. So there's a vertex that taking a lot of edges. These are called high degree vertices. And the one level, the one sentence summarize of this part is completely different from what we have covered in this second part. It's a completely different like algorithmic framework. And we'll be encounter different type of clusters, like small clusters, which are just the clusters with like size significantly different by a factor, but also flower clusters, which is like this. It's sort of single at a single point, which is just this very high crazy degree point. And also wide instance. It's based on like characterizing whether all these crazy vertices are they well connected together. If they are not, we cut them so that each of them contains one high degree vertex, and we may be able to create a flower clusters around it, and we decompose it into petals. This is how we get subinstances. And the disengagement procedure are also quite different. Now it's cycle based. And yeah, basic and advanced, we still use them throughout. Okay. Basically, what we have covered so far is the first part. Hopefully, you make some intuition of how algorithm looks like. Okay. Yeah, that's all the things that I want to cover for the second part. And in the end, I hope that it convinced you that in the second part, we can achieve a N2-1 approximation for this part. So it's combined with the previous framework, the reduction to this new problem, it gives it N2-1 approximation. Okay, and some future directions is it would be great to eventually improve this N2-1 to polylog. But so far, our algorithm has several components that are hierarchical based, so recursive based, so it's still far from getting polylog. And what about the same thing for rotation system? Actually, they are sort of equivalent because they're different by a polylog factor based on our reduction. Okay, thank you very much.
Questions?
So for the bounded degree, so your result works with the bounded degree assumption, right?
Yeah.
And you said somewhere in the argument that you're actually okay with as long as one vertex isn't too crazy. Is that true for the full theorem, or are there other places where?
So some vertex has crazy degree. This is all for the second part. The graph we start at the very beginning, they still need to be degree bounded.
So there are other places where you need it.
I mean, in the first part, the whole first part, the reduction part, rely on the graph being bounded degree. It's just the second part we. So yes, so some comments is, yeah, even it seems like the class of bounded degree graph is a special one. I believe it still captures the very complicated structure of this crossing number problem itself. So starting from this bounded degree to the general case, I believe this is still the hardcore part.
What if you allow 3 edges to cross on a single point, or I don't know, k edges to cross on a single point? Do you get a better result, or is there a fine criteria for all of these?
So you mean k is sort of a constant of your choice, or just can be arbitrary number of vertex edge count?
Let's say constant.
Yeah, so constant, it does not probably make a big difference because it's really just let's say 3 edges crossing at the same point. If you split them, it gives you 3 crossings. So it's like 3 approximation. That's, yeah, if you allow 10 edges to cross at the same point, then it's 100 approximation. You split them. And this is just some pre-request that you have to draw it in a clear way. If you allow arbitrary number of edges crossing at the same point, this may change a lot. It might be the case that you can draw it all edges that go through this single point and go somewhere else they has to, and the whole graph is just maybe 1 or 2 crossings. Then the problem becomes not very interesting.
But there might be a lot to explore. I don't know between.
Yeah,
I don't know.
Yeah, I do not know.
And psychologically, it may be easier to design things.
Okay, so let's say if you want to draw a clique, okay, you can just create a new black hole and all edges go through it. It's just 1 cross.
If there isn't.
Yeah, the problem becomes interesting.
More questions? Thanks again, sir.